All right, so today we're going to talk about classifying acids and bases, and we're really going to classify them in terms of whether they're strong or weak, and then the difference between an acid and a conjugate acid, and a base and a conjugate base. So what we need to know is that the word strong, whether we're talking about acids or bases, means complete dissociation. So that means that the ions that make up our acid or the ions that make up our base are completely breaking apart when they are put into water. Weak acids partially dissociate, meaning that they partially come apart. Now, it's not that you can separate just a little, it's that some of the molecules are going to separate and others of them are going to stay together. Here are our strong acids: HCl, HBr, H2SO4, HClO4, Hi, HNO3, HClO3. All other acids are weak. These are only strong acids. So an example of a weak acid can be acetic acid, HC2H3O2. That would be an example of a weak acid. Okay, so what does this complete dissociation mean and partial dissociation? Let's pretend that we are putting in 3 HCl compounds into our beaker of water. When we put these 3 HCl's into here, every single one of them is going to break up into H plus, Cl minus, H plus, Cl minus. The more hydrogen ions that you have in solution, the lower the pH, meaning that it's very acidic. So our strong acids create very acidic solutions because there are a lot of hydrogen ions that are in solution. Let's say we had 3 acetic acids. Because it is a weak acid, not all 3 of them are going to break apart. Maybe just one of them breaks apart. So we have H plus C2H3O2, but the other ones stay together, stay in that compound instead of breaking up into their ions. So now we only have one H plus that is in solution. It will still be acidic, so our pH will still be less than 7, but it's not going to be quite as low of a pH as this quantity of pH. Okay, so that's the difference between a strong acid and a weak acid. Same exact thing applies to strong base, but instead of having H pluses, now we're talking about OHs, so our hydroxide ions. So strong bases completely dissociate, weak bases partially dissociate. Our weak bases are those bases that have a hydroxide ion at the end and pair up with our alkali metals or some of our alkaline earth metals. All others are weak. A very common weak base is ammonia. And again, the same thing happens if we were to put, for instance, NaOH into a beaker of water. Every single one of them is going to break up into our sodium ion and our hydroxide ion. Whereas if we were to put ammonia into a solution, some of them will stay together and others of them will gain a hydrogen and become NH4+. So that's the difference between a strong base and a weak base. Just the number of bases that are breaking apart or forming new compounds. The next thing that we need to talk about are conjugate acids and conjugate bases. Basically, the only difference is the side of our reaction arrow that they're on in a balanced chemical reaction. An acid is on the reactant side of the reaction. A conjugate acid is on the product side of the reaction. Same thing for bases and conjugate bases. Your base is on the reactant side of the reaction, and your conjugate base is on the product side of the reaction. What's important to know that the acid on your reactant side turns into the conjugate base on your product side. The base on your reactant side turns into the conjugate acid on your product side. So let's look at 3 examples. Here, we want to compare hydrochloric acid to what it looks similar to on the product side. So that is our Cl. And if we use our Bronsted-Lowry definition, we know that when a compound loses a proton, so loses a hydrogen, it means that it's our acid. Okay? Now, if we look at water compared to what it looks similar to, our hydronium, here we gained a proton. So that is the Bronsted-Lowry definition of a base. So here's our acid and here's our base. Now, the way that we figure out that our acid turns to the base is because it acts like the base on the product side. So let's pretend that this was flip-flopped. If we were looking at it in the other direction, our Cl- would be gaining that hydrogen. So it's acting like a base on this side if this were a double-sided arrow. And so this is our conjugate base. Hydronium is going to be losing a hydrogen, and that's what acids do. So that on this side acts like our conjugate acid. So it's just, if we're going in the forward direction, which one's acting like the acid and the base? If we're going in the reverse direction, which one's acting like the acid and base? So let's go ahead and look at this one. H2CO3 looks similar to HCO3 minus. So in order to get from here to here, we lost a hydrogen, which means that this is our acid, which means that this is our conjugate base. Water gained a hydrogen here, which is the definition of a base, so that makes water our base again. Our bases turn into conjugate acids. Last example, H2SO4. If we look, that is similar to HSO4 minus. So to get from our reactants to our product side, our H2SO4 lost a hydrogen, it lost a proton. So again, that is an acid. Water looks similar to hydronium, and it gained a hydrogen. So that makes it the base. Now, if we're going in the opposite direction, hydronium to get to water would have to lose a hydrogen. So that means that it would be the conjugate acid. HSO4 minus would have to gain a hydrogen to go to the other side. So that would be a conjugate base. All right. Last thing for this video, something called amphoteric species. Amphoteric species is a compound that can act like an acid or base because it can either gain a hydrogen or lose a hydrogen. A very common example of this is water. Water has the ability of losing a hydrogen. If we subtract the hydrogen ion from it, it becomes OH minus. So losing a hydrogen is an example of when it acts like an acid. But if it were to gain a hydrogen, it would become our hydronium ion. And gaining a hydrogen is a property of a base. HSO4 minus. Since it has a minus on it, that tells us that it has the possibility of gaining something that has a plus charge, right? Because hydrogen in its ion form has a plus charge. So here it can become H2SO4. And it would be acting like a base here because it picked up that hydrogen. Or it can act like a base by losing that hydrogen. So it would become SO4 minus 2. It lost another plus charge, so it becomes even more negative, becoming SO4 negative 2 instead of negative 1 like it was before. Oops, sorry. Acid. Okay. H2PO4 minus. If we want it to be a base, it's going to have to gain a hydrogen, so that becomes H3PO4. And if we want it to become or act like an acid, that means that it has to be losing a hydrogen, and so it becomes HPO4 minus 2. This one can actually lose another hydrogen. So this can act like an acid again by losing another hydrogen and become PO4 minus 3. So again, an amphoteric species is one that can either gain a hydrogen or lose a hydrogen and can act like an acid or a base.